The world's telescopes are locked on the heavens as a cosmic mystery returns. Oumuamua, the bizarre interstellar object that stunned scientists in 2017, is back in the headlines, and this time, it's making waves with signals and behavior no one can explain. Is it just a strange rock, or could it be something far more extraordinary? Today on Sci and Why, we're diving deep into the latest discoveries, wild theories, and the global debate over whether Oumuamua is a messenger from beyond or a puzzle that will keep us guessing for generations. The first encounter, a visitor like no other. In October 2017, astronomers spotted something racing through our solar system so fast and so strangely shaped, it defied every expectation about what space rocks should look like. Oumuamua was the first confirmed interstellar object to visit our solar system, discovered by the Pan-STARRS 1 telescope in Hawaii. Unlike any asteroid or comet ever observed, it was extraordinarily elongated, at least 10 times longer than it was wide, and tumbled end over end as it sped past the sun at 196,000 miles per hour. Its reddish surface and cigar-like shape immediately set it apart from typical space debris. The object's hyperbolic trajectory proved it wasn't gravitationally bound to our solar system, making it a true visitor from another star system. Scientists had only weeks to study it before it disappeared into the cosmic void, but what they discovered challenged fundamental assumptions about interstellar objects. No comet tail, no visible outgassing, and most puzzling of all, an unexplained acceleration that seemed to defy the laws of physics as we understand them. The shape that launched 1,000 theories. How could a natural object be shaped like a cosmic cigar, spinning through space with dimensions so extreme that some scientists wondered if it was hollow inside? Oumuamua's extraordinary shape became its most defining and controversial characteristic. Observations revealed it measured approximately 1,300 feet long, but only 130 feet wide, a 10-to-1 ratio unprecedented in known asteroids or comets. As it rotated every 7.3 hours, its brightness varied dramatically, suggesting either an extremely elongated shape or a flat, pancake-like structure. Some researchers proposed it was a fragment from a shattered planet blasted apart by a stellar collision billions of years ago. Others suggested it might be a thin, sail-like object, perhaps even thinner than paper, which could explain its unusual acceleration through solar radiation pressure. The object's density calculations puzzled scientists further, leading to speculation about internal voids or an entirely different composition than expected. Harvard astronomer Loeb controversially suggested the shape was consistent with artificial construction, sparking heated debates about whether natural processes could create such an extreme geometry. The mystery deepened when computer models struggled to explain how such a shape could survive the violent journey between star systems. The acceleration mystery, natural or artificial. As Oumuamua sped away from the sun, it accelerated in ways that violated every known law of celestial mechanics, leaving scientists scrambling for explanations. The most perplexing aspect of Oumuamua's behavior was its non-gravitational acceleration. It sped up as it moved away from the sun, despite showing no visible signs of comet-like outgassing. Traditional comets accelerate due to jets of vaporizing ice and dust, but Oumuamua displayed no tail, no coma, and no detectable gas emissions. This acceleration was small but measurable, requiring some unknown force to explain the deviation from its predicted orbit. Scientists proposed various theories: invisible hydrogen outgassing, solar radiation pressure on an ultra-thin object, or even magnetic interactions with the solar wind. However, each explanation faced significant challenges. The hydrogen theory required the object to be made of pure hydrogen ice, which seemed unlikely given its surface properties. The solar sail hypothesis demanded an impossibly thin structure that somehow survived interstellar travel. Some researchers suggested the acceleration might result from internal heat causing asymmetric outgassing, but no evidence supported this theory. The mystery remains unsolved, with each proposed explanation raising new questions about Oumuamua's true nature and origin. The signal hunt. Are we receiving messages? When radio telescopes around the world turned toward Oumuamua, the search for artificial signals became, well, a global obsession that captured headlines and sparked wild speculation. The Breakthrough Listen project, funded by billionaire Yuri Milner, immediately targeted Oumuamua with powerful radio telescopes, scanning for any signs of artificial transmissions. Using the Green Bank telescope in West Virginia, scientists monitored the object across multiple frequency bands, searching for structured signals that might indicate an intelligent origin. While no confirmed artificial signals were detected, the very act of searching fueled public imagination, and honestly, a lot of conspiracy theories. Social media exploded with claims of hidden NASA data, secret communications, and government cover-ups. Podcasters and YouTubers, including Joe Rogan, amplified speculation about possible alien messages, often mixing legitimate scientific uncertainty with, some pretty unfounded claims. The scientific community remained cautious, emphasizing that the absence of detected signals didn't rule out artificial origin. Any advanced civilization might use communication methods beyond our current detection capabilities. Some researchers suggested that if Oumuamua was indeed a probe, it might be in listening mode rather than actively transmitting. The signal hunt really highlighted humanity's deep desire to make contact with extraterrestrial intelligence, even as it demonstrated the challenges of distinguishing between natural phenomena and potential alien technology. The Loeb hypothesis, alien technology in our backyard. When Harvard's top astronomer publicly declared that Oumuamua might be an alien spacecraft, the scientific community erupted in controversy that honestly continues to this day. Dr. Avi Loeb, chair of Harvard's astronomy department, made headlines worldwide by suggesting Oumuamua could be a piece of extraterrestrial technology, specifically a light sail or probe sent by an alien civilization. In his book, Extraterrestrial, Loeb argued that the object's unusual properties, its extreme shape, lack of outgassing, and mysterious acceleration, were more consistent with artificial construction than natural formation. He proposed that Oumuamua might be a defunct piece of alien technology, kind of like space junk from an advanced civilization drifting through the galaxy for millions of years. Loeb's hypothesis sparked fierce debate among astronomers, with many colleagues criticizing his conclusions as premature and sensationalized. Critics argued that extraordinary claims require extraordinary evidence, and that natural explanations, however unlikely, should be exhausted before invoking alien technology. Loeb countered that the scientific community's reluctance to consider extraterrestrial possibilities reflected a conservative bias that could blind researchers to genuine discoveries. His advocacy for the alien hypothesis brought unprecedented media attention to Oumuamua, transforming a scientific puzzle into a cultural phenomenon that still influences public perception of the search for extraterrestrial life. The return phenomenon, new visitors, new questions. In 2019, astronomers discovered 2I/Borisov, the second confirmed interstellar visitor, proving that Oumuamua wasn't a one-time cosmic accident but part of a larger phenomenon. The discovery of Comet 2I/Borisov by amateur astronomer Gennady Borisov demonstrated that interstellar objects regularly visit our solar system, though most likely go undetected. Unlike Oumuamua, Borisov behaved like a typical comet, displaying a clear tail and predictable outgassing patterns. This normal behavior made Oumuamua's anomalies even more striking by comparison. Advanced sky surveys like the Catalina Sky Survey and Linear are now detecting more interstellar candidates, suggesting these cosmic visitors arrive more frequently than previously thought. The upcoming Vera C. Rubin Observatory promises to revolutionize interstellar object detection, potentially finding dozens of Oumuamua-like objects each year. Each new discovery provides opportunities to test theories about interstellar object formation, composition, and behavior. Scientists are developing rapid response protocols to maximize observation time for future visitors, including potential space missions to intercept and study these objects up close. The European Space Agency has proposed the Comet Interceptor mission, which could be redirected to study an interstellar visitor if one arrives at the right time. As detection capabilities improve, researchers expect to build a comprehensive catalog of interstellar objects, potentially revealing whether Oumuamua represents a unique anomaly or part of a diverse population of cosmic wanderers. The Joe Rogan Effect: Pop Culture Meets Cosmic Mystery. When Joe Rogan's podcast featured Oumuamua discussions, millions of listeners were introduced to the possibility that aliens might have already visited our solar system. Joe Rogan's influential podcast platform amplified Oumuamua's story far beyond academic circles, bringing the interstellar mystery to mainstream audiences worldwide. Rogan's conversations with guests like Avi Loeb and other researchers transformed complex astrophysics into accessible discussions about alien visitation and government transparency. The podcast's massive reach, over 11 million listeners per episode, meant that Oumuamua became a household name, sparking dinner table debates and social media discussions about extraterrestrial life. Rogan's approach, mixing scientific curiosity with healthy skepticism about official narratives, really resonated with audiences hungry for alternative perspectives on space exploration. The Joe Rogan effect demonstrated how modern media can rapidly transform scientific discoveries into cultural phenomena, sometimes even faster than peer review processes can validate or debunk emerging theories. While some scientists worried about misinformation spreading through popular media, others appreciated the increased public interest in astronomy and space science. This phenomenon highlighted the complex relationship between scientific research, media coverage, and public understanding of cosmic mysteries. Oumuamua's story became intertwined with broader discussions about UFO disclosure, government secrecy, and humanity's place in the universe, showing how a single astronomical discovery can capture the collective imagination and influence cultural conversations about our cosmic future. The message hypothesis. What if we're being contacted? If Oumuamua really is an alien probe, what message might it be trying to deliver, and would humanity even recognize an extraterrestrial communication if we received one? The possibility that Oumuamua represents an intentional message from another civilization raises some pretty profound questions about interstellar communication and, honestly, about human readiness for contact. If the object is indeed artificial, its mere presence in our solar system could be the message itself, a demonstration that interstellar travel is possible and, well, that we are not alone. Some researchers speculate that an advanced civilization might use physical objects as information carriers, encoding data in their structure, composition, or behavior patterns. The object's unusual trajectory, taking it close to the Sun and through the inner solar system, might be designed to ensure detection by any technologically capable species. Scientists have proposed that future interstellar visitors should be examined for microscopic structures, isotopic signatures, or other indicators of artificial construction. The challenge lies in recognizing alien technology that might operate on principles entirely foreign to human understanding. If Oumuamua is a probe, it might be conducting its own observations, gathering data about our solar system, planet, and civilization. The object's tumbling motion could be intentional, allowing sensors to scan in all directions as it travels. Some theorists suggest that the probe might be waiting for a specific signal or technological milestone before activating communication protocols, making humanity's response crucial for future contact. The scientific response. New tools, new discoveries. Armed with next-generation telescopes and AI-powered detection systems, astronomers are preparing for the next Oumuamua, and this time, they'll be ready to unlock its secrets. The Oumuamua encounter really revolutionized how scientists approach interstellar object detection and study. The upcoming Vera C. Rubin Observatory will scan the entire visible sky every few nights, potentially detecting interstellar objects weeks or even months before they reach their closest approach to the Sun. This early warning system will provide unprecedented opportunities for detailed study, including spectroscopic analysis, radar observations, and even potential space missions. NASA and ESA are developing rapid response protocols for interstellar visitors, including pre-positioned spacecraft that could be quickly redirected to intercept interesting objects. Advanced AI algorithms are being trained to identify unusual orbital characteristics that might indicate artificial origin, automatically flagging objects for priority observation. The James Webb Space Telescope's infrared capabilities could reveal surface composition and thermal properties invisible to optical telescopes. Scientists are also developing new theoretical frameworks for understanding how natural interstellar objects form and evolve, providing better baselines for identifying truly anomalous visitors. International collaboration networks are being established to coordinate global observations and share data in real time. The next interstellar visitor will face the most comprehensive scientific scrutiny in history, potentially finally answering whether objects like Oumuamua represent natural phenomena or something far more extraordinary. The legacy of Oumuamua, a new era of cosmic awareness. Whether Oumuamua was a space rock or an alien probe, its brief visit fundamentally changed how humanity views our place in the galaxy and our readiness for contact. Oumuamua's legacy extends far beyond its physical properties or mysterious behavior. It represents a paradigm shift in human consciousness about our cosmic environment. The object's visit demonstrated that our solar system is not isolated, but part of a dynamic galactic ecosystem where matter, and potentially information, flows between star systems. It forced scientists to confront the limitations of current theories about planetary formation, interstellar travel, and the prevalence of life in the universe. The controversy surrounding its interpretation highlighted the tension between scientific conservatism and the need for open-minded inquiry when confronting unprecedented phenomena. Public fascination with Oumuamua revealed humanity's deep yearning for cosmic connection and our readiness to consider the possibility of extraterrestrial intelligence. The object's story became a catalyst for increased funding in SETI research, interstellar object detection, and astrobiology programs worldwide. Educational institutions began incorporating interstellar visitor scenarios into their curricula, preparing the next generation of scientists for a universe that might be far more active and populated than previously imagined. As we await the next interstellar visitor, Oumuamua's mystery continues to inspire scientific research, artistic expression, and philosophical reflection about humanity's cosmic future and our potential place in a galaxy teeming with intelligence. Oumuamua's journey through our solar system has left us with more mysteries than solutions. But that's what makes science so thrilling. Whether it's a cosmic rock, an alien probe, or something we haven't even imagined, its story challenges us to stay curious and keep exploring. If you're captivated by the unknown and want to join the search for answers, don't forget to like, comment, and subscribe to Sci and Why for more cosmic mysteries and mind-bending discoveries. Thanks for watching. Stay tuned for the next interstellar visitor. On September 26, 2022, NASA achieved something truly unprecedented. They deliberately crashed a spacecraft into an asteroid at 6.6 kilometers per second and, get this, completely changed its orbit. The DART mission wasn't just about proving we could hit a space rock. No, it was humanity's first successful test of planetary defense technology. But what happened after the collision honestly shocked scientists and revealed truths about asteroids that nobody really expected. The aftermath of this cosmic collision is rewriting everything we thought we knew about protecting Earth from space threats. The journey to impact. NASA's Double Asteroid Redirection Test, or DART, began its historic journey on November 24, 2021, launching from Cape Canaveral Space Launch Complex 40 atop a SpaceX Falcon 9 rocket. The refrigerator-sized spacecraft traveled for nearly 10 months across 11 million kilometers of space to reach its target, a small asteroid moonlet called Dimorphos. The mission team, led by project scientist Dr. Nancy Chabot at the Johns Hopkins Applied Physics Laboratory, had meticulously planned every detail of this unprecedented experiment. Unlike previous space missions that aimed to study celestial objects, DART was designed with one purpose: to slam into Dimorphos and change its orbital path around the larger asteroid Didymos. The spacecraft carried advanced navigation systems that would allow it to autonomously guide itself to impact during the final 4 hours of flight, since the 11-minute communication delay with Earth made real-time control totally impossible. As DART approached its target, onboard cameras captured dramatic images of the asteroid growing larger and larger, marking humanity's first intentional collision with another world for planetary defense purposes. The perfect target. Dimorphos proved to be the ideal testing ground for this groundbreaking experiment, measuring approximately 160 meters in diameter and orbiting its larger companion Didymos every 11.9 hours. The binary asteroid system, located about 11 million kilometers from Earth at the time of impact, posed no threat to our planet, making it a safe target for this high-stakes test. Didymos, the larger asteroid measuring 780 meters across, served as the gravitational anchor for its smaller moonlet. Scientists chose this system because any change in Dimorphos's orbit could be precisely measured from Earth, using ground-based telescopes and radar systems. The asteroid pair was discovered in 1996, and had been extensively studied, providing researchers with detailed baseline measurements of their orbital characteristics. The proximity of the two asteroids meant that even a small change in Dimorphos's velocity would produce a measurable shift in its orbital period around Didymos. This binary system represented the perfect natural laboratory for testing kinetic impactor technology, close enough to Earth for accurate observation, large enough to produce detectable changes, yet far enough away to ensure complete safety for our planet throughout the experiment. The moment of impact. At exactly 23:14 UTC on September 26, 2022, DART slammed into Dimorphos at a closing speed of 6.14 kilometers per second, releasing kinetic energy equivalent to approximately 2.5 tons of TNT. The collision occurred with pinpoint accuracy, striking the asteroid's surface and instantly vaporizing the 610-kilogram spacecraft along with a portion of the asteroid's rocky material. Ground-based telescopes around the world captured the dramatic moment as a brilliant flash of light erupted from the impact site, followed by an expanding cloud of debris that grew brighter over several hours. The Hubble Space Telescope and James Webb Space Telescope immediately began observing the aftermath, documenting the evolution of the ejecta plume as it stretched across thousands of kilometers of space. Within minutes of impact, the debris cloud had expanded beyond Dimorphos itself, creating a spectacular tail of material that resembled a comet's tail stretching behind the asteroid. Amateur astronomers joined professional observatories in tracking the collision's effects, witnessing history as humanity demonstrated its ability to alter the path of a celestial object. The impact created seismic waves that rippled across Dimorphos' surface, potentially reshaping the asteroid's internal structure in ways that scientists are still working to understand. Beyond all expectations. The results of the DART impact exceeded every prediction and shattered the mission's success criteria. Instead of the minimum 73-second change in orbital period that would have declared the test successful, Dimorphos' orbit around Didymos shortened by an astounding 32 minutes. This dramatic change represented a 26-fold improvement over the mission's baseline requirements, proving that kinetic impactor technology was far more effective than scientists had dared to hope. The massive orbital change resulted not just from the direct momentum transfer of the spacecraft's impact, but from the unexpected efficiency of the momentum multiplication effect created by the ejected debris. As material blasted away from the impact site, it carried additional momentum in the opposite direction, acting like a natural rocket engine that amplified the deflection effect. Dr. Tom Statler, DART program scientist at NASA, described the results as a watershed moment for planetary defense and humanity's ability to influence our cosmic environment. The orbital change was so significant that it could be measured by small telescopes and even confirmed by radar observations from Arecibo Observatory and the Goldstone Deep Space Communications Complex. This level of deflection meant that if Dimorphos had been on a collision course with Earth, the impact would have shifted its trajectory by hundreds of thousands of kilometers. The mysterious ejecta cloud. The debris cloud created by DART's impact revealed secrets about asteroid composition that puzzled scientists worldwide. Instead of the uniform dust plume that computer models predicted, the ejecta displayed complex structures including multiple debris streams, spiral patterns, and irregular particle distributions that suggested Dimorphos had a far more complex internal structure than anticipated. Dr. Christina Thomas at Northern Arizona University, who led the observational campaign, noted that the debris cloud evolved in unexpected ways over the following weeks. Some particles were ejected at speeds exceeding 500 meters per second, while others moved much more slowly, creating distinct populations of material with different trajectories and behaviors. The cloud's asymmetric shape indicated that Dimorphos wasn't a solid uniform rock, but likely a rubble pile, a loose collection of smaller rocks and boulders held together by weak gravitational forces. High-resolution images from ground-based telescopes revealed that the ejecta contained both fine dust particles and larger chunks of material, some potentially meters in size. The debris cloud's brightness variations suggested that different types of material were being ejected from various depths within the asteroid, providing unprecedented insights into the internal layering and composition of small solar system bodies. Hera's investigative mission. Recognizing the need to understand DART's impact in detail, the European Space Agency launched the Hera mission in October 2024 to conduct a comprehensive post-impact investigation. This follow-up mission represents an unprecedented example of international cooperation in planetary defense, with Hera scheduled to arrive at the Didymos system in late 2026 to examine the crater left by DART's collision. The spacecraft carries advanced instruments including high-resolution cameras, thermal imagers, and radar subsystems designed to map both asteroids down to centimeter-scale resolution. Hera will measure the precise size and depth of DART's impact crater, analyze the composition of exposed subsurface material, and determine how the impact altered the internal structure of both Dimorphos and its parent asteroid Didymos. The mission will also deploy 2 small CubeSats called Juventus and Milani to conduct complementary investigations, including the first radar sounding of an asteroid's interior and detailed gravitational field mapping. Dr. Patrick Michel, Hera's principal investigator, emphasized that understanding the physical properties revealed by DART's impact is crucial for designing future deflection missions. The data collected by Hera will validate computer models used to predict deflection effectiveness and provide the foundation for operational planetary defense systems. Unraveling asteroid mysteries. The DART impact revealed that small asteroids like Dimorphos are far more complex than scientists previously understood, fundamentally changing how we think about these cosmic building blocks. Pre-impact models assumed asteroids were relatively simple objects with predictable responses to external forces, but the dramatic success of the deflection demonstrated that rubble pile asteroids behave more like fluid structures than solid rocks. Dr. Andy Rivkin at the Johns Hopkins Applied Physics Laboratory noted that the impact's efficiency suggested Dimorphos has very low internal cohesion, allowing the impact energy to propagate throughout the entire structure and eject material from multiple locations. The asteroid's surface appears to be covered in loose regolith, fine, rocky debris accumulated over millions of years, that was easily disturbed by the impact's shockwaves. Spectroscopic observations of the ejecta revealed that Dimorphos contains ordinary chondrite minerals, similar to the most common meteorites found on Earth, but with unusual proportions that suggest a complex formation history. The impact also provided insights into how small asteroids respond to tidal forces from their parent bodies, with evidence suggesting that Dimorphos experiences ongoing surface changes due to its proximity to Didymos. These discoveries have profound implications for understanding asteroid evolution, the formation of binary systems, and the potential resources available on near-Earth asteroids for future space missions. Complications for future defense. While DART proved that kinetic impactors can deflect asteroids, the mission also revealed complications that will influence future planetary defense strategies. The unexpectedly large orbital change, while impressive, highlighted just how difficult it is to predict exactly how different asteroids will respond to impact. Dr. Nancy Chabot emphasized that the momentum multiplication factor, the ratio of total momentum change to the spacecraft's initial momentum, varied significantly from pre-impact predictions, reaching values between 2.2 and 4.9 depending on the measurement method. This variability means that future deflection missions will require detailed advanced characterization of target asteroids to predict their response accurately. The complex ejecta pattern suggested that asteroid internal structure, surface composition, and rotation state all influence deflection efficiency in ways that current models just don't fully capture. The discovery that small asteroids behave more like loosely bound rubble piles than solid objects means that deflection strategies must account for potentially dramatic differences in material properties between different asteroid types. Mission planners now recognize that successful planetary defense will require a library of deflection techniques tailored to specific asteroid characteristics, rather than a one-size-fits-all approach. The DART results also emphasize the importance of early detection and characterization, since deflection effectiveness depends critically on understanding an asteroid's physical properties years before any potential impact threat. Global Planetary Defense Initiative. The success of the DART mission has catalyzed unprecedented international cooperation in planetary defense, transforming what was once considered science fiction into practical space policy. NASA's Planetary Defense Coordination Office, established in 2016, now works closely with the European Space Agency, Japan's JAXA, and other international partners to develop comprehensive strategies for detecting and deflecting hazardous near-Earth objects. The United Nations Office for Outer Space Affairs has established new protocols for sharing asteroid tracking data and coordinating deflection missions, recognizing that planetary defense is a global responsibility requiring multinational collaboration. Ground-based survey telescopes like the Catalina Sky Survey in Arizona and the Linear program in New Mexico continue discovering new potentially hazardous asteroids at rates exceeding 1,000 per year, building a comprehensive catalog of objects that might someday threaten Earth. space-based detection systems including NASA's NEOWISE mission and the planned NEO Surveyor telescope will dramatically improve our ability to find and track smaller asteroids that ground-based systems might miss. The establishment of the International Asteroid Warning Network ensures that discovery data reaches decision-makers quickly enough to enable deflection missions if needed. These coordinated efforts represent humanity's first serious attempt to protect our planet from cosmic threats that have caused mass extinctions throughout Earth's history. The future of planetary defense. The DART mission's spectacular success has laid the foundation for humanity's first operational planetary defense system, but it also revealed how much we still need to learn about deflecting dangerous asteroids. Future missions will build on DART's legacy by testing different deflection techniques including gravity tractors, nuclear standoff detonations, and enhanced kinetic impactors designed for specific asteroid types and threat scenarios. NASA's follow-up missions are already in development, including concepts for multi-spacecraft deflection systems that could handle larger asteroids or provide backup capabilities for critical deflection attempts. The double asteroid redirection test proved that humanity possesses the technological capability to alter the course of celestial objects, marking our species' transition from passive observers of cosmic events to active participants in shaping our solar system's dynamics. Advanced computer simulations now incorporate DART's impact data to model deflection scenarios with unprecedented accuracy, enabling mission planners to design precise interventions for specific threat asteroids. The mission's success has also sparked development of rapid response deflection technologies that could be deployed on shorter timescales for newly discovered threats. Most importantly, DART demonstrated that international cooperation and scientific expertise can overcome seemingly impossible challenges, providing a template for tackling other global threats that require coordinated human action on planetary scales. So there you have it. NASA didn't just hit an asteroid, they revolutionized planetary defense and revealed that asteroids are far stranger than we imagined. Which discovery about the DART mission surprised you the most? Let me know in the comments below. If you enjoyed learning about humanity's first successful planetary defense test, make sure to like this video, share it with someone who loves real space breakthroughs, and don't forget to subscribe to Sci and Y for more incredible discoveries about our universe. Until next time, keep exploring the cosmos. Interstellar space begins where the sun's influence fades, and the solar wind finally yields to the raw plasma of the Milky Way. Since 2017 we have confirmed just 3 visitors from that vast realm, the puzzling Oumuamua, herald of surprises, volatile comet Borisov, and now the outsized newcomer 3I Atlas. Each object is a priceless sample return mission delivered for free by nature, letting us probe chemistry, structure and age far beyond the planets. Tonight we collect every solid fact astronomers have pieced together about this latest cosmic ambassador. Beyond the heliopause, our interstellar visitors. The solar system's frontier is the heliopause, a shifting magnetic shell standing roughly 18 billion kilometers from the Sun. When Voyager 1 pierced that frontier in 2012, its plasma detector confirmed the long-predicted transition into interstellar space. Densities jumped, solar origin particles vanished, and cosmic ray counts spiked. Since then, terrestrial telescopes have reverse experienced the same crossing by spotting travelers arriving from the galaxy's dark sea. The odds are daunting. Dynamical models suggest only a few hundred-meter-scale bodies wander through the inner solar system each century. Yet modern wide-field surveys and continuous sky patrols have already netted 3 confirmed interstellar objects in just 8 years. Their hyperbolic speeds, inbound directions, and inability to be captured by solar gravity reveal origins that lie light-years away. Each new detection is therefore a planetary science windfall, a primitive shard of another star's debris disk, altered by eons of irradiation and micrometeoroid pummeling, finally falling within reach of Earth's spectrographs. As instrumental sensitivity grows, researchers expect a steady trickle of similar emissaries, gradually transforming Exotica into a statistically rich field of comparative planetology. The third visitor, 3I/ATLAS discovery. On June 2025, the twin Schmidt telescopes of the Asteroid Terrestrial Impact Last Alert System swept across the pre-dawn sky and registered an object moving too fast to be bound to the Sun. Alert messages flashed from Hawaii to South Africa and onto the Minor Planet Center, where the trajectory was confirmed within hours. Principal investigator Dr. Larry Deneau announced the team had netted 3Y Atlas, humanity's third verified interstellar wanderer. Early photometry implied a remarkable diameter between 10 and 20 kilometers, at least an order of magnitude larger than Oumuamua. That sheer size promised ample reflected sunlight for spectroscopy, galvanizing observatories on 5 continents to obtain time-critical data. Infrared spectra hinted at complex organics, millimeter-wave receivers searched for exotic volatiles, radar attempted shape reconstruction when geometry allowed. The discovery also demonstrated how automated pipelines, artificial intelligence vetting, and instantaneous worldwide coordination can turn a few faint pixels into an unprecedented international campaign within a single rotation of Earth. 3. Y Atlas thus became both a scientific target and a systems engineering triumph, showing that planetary defense infrastructure doubles as an accidental interstellar object early warning net. A hyperbolic journey at 58 kilometers. Trajectory solutions from JPL's Horizon system reveal 3I Atlas, racing along a hyperbolic trajectory with an inbound heliocentric speed of 58 kilometers per second. Calculations by Dr. Davide Farnochia show the path threads the orbits of Mars and Jupiter before the object slingshots back toward the galactic northwest, never to return. That excess velocity, nearly 3 times Earth's orbital speed, guarantees the visitor is unbound. No realistic gravitational interaction could capture it. Dynamical backtracing suggests 3Y Atlas last crossed the galactic plane 30 million years ago, and may have originated near the Carina Sagittarius spiral arm, though stellar encounter uncertainties are large. During its brief stay, it will feel weak but measurable tugs from planetary masses, allowing researchers to test N-body propagation codes under extreme boundary conditions. The rapid passage also forces astronomers into a sprint. Every observing window must be filled, sometimes with instruments never before aimed at the same target in a single night. Lessons learned from these coordination drills will feed directly into mission concepts such as ESA's Comet Interceptor, designed to launch quickly toward the next unpredictable celestial visitor. Brightness, rotation, and the 29-hour cycle. Time series photometry from the Nordic Optical Telescope reveals these quasi-periodic brightness swings of about 9/10 of a magnitude. This maps onto a rotation period of, well, around 29 hours. Data from the European Southern Observatory confirm an irregular, likely elongated body. Its long axis could exceed 9 kilometers, which is quite something. Now, if we invert the light curve, it suggests an axis ratio of approximately 3:1. This is comparable to Oumuamua's extreme proportions, but on a much grander scale. The stability of this amplitude argues against the idea of loose rubble. Instead, it seems that 3I/Atlas might possess a cohesive monolithic core. This core is likely overlain by mantling regolith that accumulated during its galactic journey. Surface scattering models propose alternating patches of dark carbonized crust and brighter, possibly icy facets. These rotate into sunlight, driving the observed flux pattern. Continued monitoring aims to detect Yorp-induced spin-up or subtle precession. These phenomena could reveal internal density gradients. Polarimetric measurements planned for perihelion will test whether charged particle implantation or interstellar UV processing has glassified surface grains, a state never observed on indigenous comets. So, every rotational cycle opens a time-lapse window onto geological processes, operating far beyond the reach of any spacecraft. Coma, tail, and cometary activity. Solar heating at 1.5 astronomical units would normally trigger vigorous sublimation in an ice-rich nucleus. Yet, the Spitzer Space Telescope detected only a whisper of carbon monoxide and carbon dioxide. Lead investigator Dr. Colin Snodgrass suggests that cosmic ray gardening over millions of years may have sintered 3I/Atlas's upper meters into an insulating crust. This crust throttles volatile escape. Ground-based narrowband filters isolate a tenuous cyanogen halo, but production rates are nearly 2 orders of magnitude below those of Comet Borisov at a comparable distance. Radar attempts from Goldstone found no large dust grains, which is consistent with a surface depleted in friable material. The resulting weak coma and filamentary tail defy classical comet models. This suggests either an unusual primordial composition or extreme evolutionary processing. Should deeper layers ever fracture, a sudden jet could alter the trajectory. This would offer a real-time test of non-gravitational forces on an interstellar scale. Monitoring continues around the clock because even a modest outburst would provide precious gas for isotopic assays. This could potentially distinguish whether the body formed around a metal-poor population 2 star or within a young planet-forming disk more like our own nebular cradle. Oumuamua versus Borisov versus 3I/Atlas. Comparative planetology now has 3 data points beyond the heliopause. Oumuamua, flagged in 2017, was a cigar-shaped 200-meter object. It had perplexing non-gravitational acceleration but no detectable gas. Borisov erupted in 2019 with classical dust jets rich in carbon monoxide and hydrogen cyanide. It behaved like a solar system comet transplanted intact. In contrast, 3I/Atlas is 10 times larger than Oumuamua. It shows Borisov-style composition signatures only faintly and rotates slowly. Together, they outline a spectrum of possibilities: dormant shard, pristine comet, and massive, highly processed giant. Spectral slopes vary from Oumuamua's red, organic-rich hue to Borisov's more neutral tones. 3I/Atlas sits in between, pointing to mixed ice rock interiors masked by millennia of irradiation. Dynamically, all 3 arrived on different galactic vectors, indicating no shared parent system. The trio's collective diversity is reshaping models of planetesimal ejection. This implies that every maturing planetary system may fling out thousands of distinct fragments, icy, rocky, or hybrid, into interstellar exile. Future detections by Rubin Observatory will determine whether our current sample is typical or a statistical fluke driven by small number bias and selection effects. A 3 billion 11-year-old traveler. Isotope ratio modeling and cosmic ray exposure calculations, bracket 3I Atlas's formation epoch between 3 and 11 billion years, actually predating the Sun at the upper bound. High-energy proton bombardment gradually converts surface ice to complex refractory organics, which leads to the dark, reddish spectra seen in long-aged Kuiper Belt objects, and similar signatures adorn our visitor. Laboratory analogs produced under accelerator beams match the object's infrared absorption bands, supporting an ancient surface residency in the galactic field. Queen's University Belfast researcher Dr. Alan Fitzsimmons notes anomalously low crystalline ice features, implying the body spent little time near its natal star before ejection. Over gigayears, random supernova shocks, molecular cloud passages, and gravitational nudges from passing stars sculpted its current orbit, effectively sandblasting volatile layers while leaving mineral matrices intact. Each detected molecule, therefore, archives conditions from epochs otherwise inaccessible to observation. Studying such relics refines timelines for disk evolution, migration, and dynamical instability in alien solar systems. With only 3 interstellar samples so far, every additional chemical clue counts exponentially toward mapping the history of matter across the Milky Way. October 30th, perihelion and beyond. On October 30th, 2025, 3I/Atlas skimmed within just over 1 astronomical unit of the Sun, a geometry that placed it high in the northern skies. The James Webb Space Telescope devoted emergency directors discretionary time to obtain mid-infrared spectra, capturing silicate emission features rarely obtainable for interstellar bodies. Coordinated campaigns linked Subaru's visible light spectrograph, ALMA's sub-millimeter receivers, and amateur CCD networks into a single global array. The perihelion distance of 1.1 astronomical units allowed measurement of thermal inertia by tracking flux changes over the 29-hour rotation, constraining surface conductivity and porosity. Lead organizer Dr. Casey Lisi reports negligible change in gas production rates pre- and post-perihelion, bolstering the processed crust hypothesis. Hubble imaging after the closest approach detected a faint meteoroid trail, suggesting low-level dust loss perhaps triggered by microfractures. Precise astrometry during solar conjunction refined mass estimates via non-gravitational drift constraints, yielding a bulk density around 1.8 grams per cubic centimeter, denser than comet nuclei but lighter than stony asteroids. As 3I/Atlas recedes, radar pings and thermal mapping will continue until signal-to-noise evaporates, freezing an irreplaceable dataset for decades of post-mission analysis. Future observations and scientific opportunities. The forthcoming Vera C. Rubin Observatory promises to transform fleeting luck into routine science, with its legacy survey of space and time projected to discover dozens annually of interstellar objects as faint as 24th magnitude. pipeline architect Dr. Michelle Bannister is configuring machine learning classifiers to flag hyperbolic motion within hours, enabling rapid response spectroscopic triage. Complementary radio searches at FAST and Meerkat will probe for OH masers produced when unprocessed ices meet sunlight, while ESA's proposed Comet Interceptor could be retargeted to chase the next sizable wanderer. Astrodynamicists are refining solar sail trajectories capable of 5 astronomical units per year departures, potentially intercepting outbound objects for close-up imaging or sample capture. Coupled with isotope microanalysis, such missions would revolutionize understanding of galactic chemical gradients, delivering ground truth unattainable by remote sensing alone. Moreover, interstellar grains embedded in Earth's atmosphere, first cataloged by NASA's Stardust mission, could be chemically matched to parent bodies like 3I/Atlas, linking macroscopic dynamics with microscopic composition. These interdisciplinary strategies will crystallize a new subfield, galactic small-body science, uniting astronomy, planetary geology, and heliophysics under a single question: how does matter move, evolve, and mingle across star systems? Conclusion and cosmic perspectives. In a single decade, humanity has advanced from 0 confirmed extrasolar planetesimals to detailed dossiers on 3, culminating in the colossal Robert Werik discovery lineage that now includes 3I/Atlas. Each arrival widens our chemical dictionary, tests dynamical models, and reminds us the solar system is porous, not isolated. The study of interstellar visitors transforms accidental alignments into deliberate natural experiments, revealing chemical signatures forged under alien suns. Ultimately, these bodies invite a profound, humbling realization. Planet formation, collision, and ejection are universal, scattering shards of distant worlds throughout the galaxy. As surveys grow sharper and propulsion methods bolder, future scientists will map these shards into a web of shared origins, dissolving the parochial notion that samples must be fetched by billion-dollar probes. Instead, the galaxy occasionally mails postcards in the form of ancient rocks, carrying isotopic clues and perhaps organic seeds. Harvesting their stories will redefine planetary science from a solar system discipline into a truly galactic understanding, linking every world, seen or unseen, into a dynamic, ever-exchanging community of matter. 3I/Atlas is already dimming, yet its data trove will inspire research for years. Whether colossal comet, irradiated asteroid, or something even stranger, it confirms our cosmos is alive with wanderers older than Earth itself. Which mystery intrigues you most? Its muted coma, ancient chemistry, or breakneck speed? Let us know in the comments. Like, share, and subscribe to Sci and Y for more journeys beyond the heliopause. Until next time, keep looking up and stay curious. For all of human history, the moon has been our silent, constant companion in the night sky. We've seen it as a deity, a destination, and, well, a dead world. But recent events have shattered that last perception. A groundbreaking discovery by China's space program has confirmed that our moon is not a static relic, but a dynamic body teeming with resources that could, honestly, redefine humanity's future, turning science fiction into scientific fact. So, what did they find, and how does it connect to the decades of mystery surrounding our moon? Let's dive in. Anomalous lunar structures. The conversation about inexplicable objects on the moon often circles back to a single pivotal mission, the 1994 Clementine mission. This was not a standard NASA science mission. It was a joint project with the United States Department of Defense's Ballistic Missile Defense Organization. Its official purpose was testing advanced lightweight sensors by mapping the moon, but its military oversight has, fueled speculation that its agenda was more than purely scientific. From the massive trove of 1.8 million digital images it sent back, a few select frames have become legendary within circles that investigate lunar anomalies. These images, especially from the perpetually hidden far side of the moon, appear to contain features that defy easy geological explanation. There are patterns that look unnervingly geometric, with straight lines and sharp 90-degree angles that some interpret as the weathered ruins of immense ancient structures. The most famous of these is a feature that strikingly resembles a massive three-sided pyramid. While the scientific consensus attributes these oddities to a combination of digital image compression artifacts and the deceptive play of light and shadow across an alien landscape, many researchers remain unconvinced. They point to what they see as signs of deliberate censorship, like patches of unnatural blurring or obfuscation, suggesting that the Clementine mission was, in fact, a reconnaissance flight to get a closer look at something that was already known to be there. Ancient astronaut connections. The intriguing possibility of lunar ruins feeds directly into the wider, captivating theory of ancient astronauts. This hypothesis suggests that intelligent extraterrestrial species have been visiting Earth for millennia, and that their influence is recorded in our oldest myths, artworks, and sacred texts. This lens reinterprets our history not as a story of primitive superstition, but of misunderstood technology. For instance, a persistent piece of UFO folklore is a supposed secret transcript from the Apollo 11 mission, where Neil Armstrong allegedly expressed shock at seeing massive alien craft and structures. A story that has been thoroughly debunked by NASA but, continues to circulate. This narrative is woven into reinterpretations of ancient texts, such as the Sumerian cuneiform tablets. In one tale, a godlike being from the Anunnaki advises his son, before a journey to the moon, to wear his eagle's mask. Proponents of the theory argue this is a clear description of a helmet, a piece of life support technology. This same re-examination is applied to ancient art across the globe, most notably the Wandjina cave paintings in Australia. These ancient artworks depict beings with large dark eyes and heads surrounded by a halo-like ring, which look remarkably similar to a modern astronaut viewed through the visor of their helmet. The question the theory poses is a powerful one. Were our ancestors painting gods, or were they painting visitors? China's groundbreaking discovery. Moving from compelling theories to verifiable facts, China's space program has recently delivered hard, verifiable evidence that is, in its own way, just as revolutionary. The nation's Chang'e 5 mission was a masterpiece of robotic engineering. In December 2020, it successfully touched down in a previously unexplored region of the moon, drilled into the regolith to collect samples from beneath the surface, and then returned 1,731 grams of lunar material to Earth. It was the first time in 44 years that humanity had brought back a piece of the moon. After more than a year of intense analysis, Chinese scientists made two monumental announcements in 2022. The first was the identification of a completely new mineral, a phosphate crystal they named Change Site Y. This placed China in an exclusive club with the United States and the former Soviet Union as one of only 3 nations to have discovered a new lunar mineral. The second discovery, however, had even more profound implications. They found definitive proof of water, not as ice, but as molecules trapped inside tiny beads of glassy material forged in the heat of ancient asteroid impacts. This finding completely changed the scientific understanding of lunar water, proving it wasn't just isolated at the frigid poles but was, in fact, distributed far more widely across the moon's surface. Revolutionary implications. So, this confirmation of widespread water on the moon is honestly a watershed moment for the future of human space exploration, because it really validates the concept of in situ resource utilization, or ISRU. That's the principle of using local materials to create what you need to survive, instead of hauling everything from Earth. For decades, the dream of a permanent lunar base just seemed totally out of reach, mostly because of the massive costs involved in launching all the water, oxygen, and fuel required. But China's discovery, well, it completely reshapes that calculation. Even though each glass bead contains only a tiny amount of water, the sheer volume of lunar soil means there could be as much as 270 billion metric tons of water up there. Future missions could send rovers to heat the soil, releasing the trapped water as vapor, which could then be collected and condensed. This water would be absolutely vital for drinking and for irrigating crops in lunar greenhouses. And perhaps even more importantly, electricity can split the water into its base components: breathable oxygen for life support, and powerful hydrogen for rocket fuel. This really transforms the moon from just a desolate stopover into a self-sufficient exploration hub, and honestly, a fully functional gas station for missions heading deeper into our solar system. The Chang'e program evolution. China's lunar triumphs aren't just the result of a single lucky mission. They're actually the culmination of a patient, multi-decade, and brilliantly executed strategy called the Chinese Lunar Exploration Program, or CLEP. This program was designed as a deliberate 3-step progression, each step more complex than the last. The first step was becoming a lunar satellite state, pulled off with the Chang'e 1 and Chang'e 2 orbiters. These missions created high-resolution maps of the entire lunar surface and identified potential landing sites for the future. The second step was achieving a surface landing, and that milestone was reached in 2013 with the Chang'e 3 mission, which deployed the U-2 rover, a major national achievement. Then China showed off its advanced capabilities with the historic Chang'e 4 mission in 2019, pulling off a world first by successfully landing on the far side of the moon. That took a dedicated relay satellite to solve the communication blackout problem. The third step, which was the most complex, was sample return. The Chang'e 5 mission nailed this in 2020, performing a landing collection, a launch from the moon, a robotic rendezvous in lunar orbit, and a safe return to Earth. This methodical step-by-step approach has really shown without a doubt that China has arrived as a top-tier space power. Resource revolution on the moon. The samples returned by Chang'e 5 have honestly unleashed a scientific revolution. They've recast our view of the moon, so it's not just a geological artifact anymore. It's a vast repository of strategic and economic resources. The discovery of the new mineral, Change Site Y, is more than just a novelty. It's significant because it's a phosphate mineral containing helium-3, which is extremely rare on Earth, but has been sprayed onto the moon's surface by the solar wind for eons, getting trapped in the top layer of regolith. A lot of physicists consider helium-3 to be the ideal fuel for nuclear fusion, which is like the holy grail of energy production. Fusion reactors powered by helium-3 could generate huge amounts of clean energy, with no greenhouse gas emissions and none of the dangerous long-lasting radioactive waste you get from today's nuclear fission plants. The ability to mine helium-3 on the moon could, one day, actually secure humanity's energy future. Beyond that, lunar soil is also rich in rare earth elements, which are vital for making everything from smartphones and electric cars to advanced defense systems. So, the moon could become a critical source for these materials, helping to ease the environmental damage and geopolitical tensions that come with mining them here on Earth. Future lunar colonization. With the confirmation of accessible water, a potential source of near-limitless energy from helium-3, and abundant construction materials, the vision of a permanent human settlement on the moon has leaped from the pages of science fiction into the formal strategic planning of major world powers. This vision took a significant step toward reality in March 2021, when China and Russia officially announced a joint partnership to build the International Lunar Research Station, or ILRS. This is a profoundly ambitious project to establish a permanent and eventually fully autonomous scientific outpost near the moon's south pole. This location is highly strategic due to the presence of large quantities of water ice believed to be trapped in its permanently shadowed craters. The ILRS is designed to be a hub for scientific discovery, technology verification, and large-scale resource extraction. It will serve as the crucial proving ground for the systems and technologies necessary to sustain human life for long durations in the harsh environment of deep space. And underscoring the seriousness of this commitment, Chinese space officials have stated their intention to have a nuclear power plant operational on the moon by 2028 to power the station's construction and early operations. Lunar resources, the new gold rush. The definitive discovery of vast and valuable resources on the moon has officially ignited a 21st-century gold rush. This has created an intense geopolitical competition to claim and control the most strategic locations, turning the lunar South Pole into the most sought-after real estate in the solar system. This land rush, however, is taking place in a dangerous legal vacuum. The foundational treaty of space law, the 1967 Outer Space Treaty, is clear on one point. It explicitly prohibits any nation from making a claim of sovereignty over the moon or any other celestial body. No one can own lunar land. However, the treaty is critically vague on the issue of resource exploitation. It does not provide a clear legal framework for whether a nation or a private company can mine lunar resources and claim ownership of them. This ambiguity has created a high-stakes race where the prevailing logic is that possession is 9/10 of the law. Nations are now rushing to establish a physical presence, to land rovers, build habitats, and demonstrate resource extraction, in the belief that these actions will establish a de facto precedent, strengthening their position in future negotiations over who gets to write the rules for the lunar economy. International space race. Today's race back to the moon is a fundamentally different beast from the two-horse race of the Cold War. It is a global, multipolar and heavily commercialized affair. One of the principal efforts is led by the United States through NASA's Artemis program. The goals of Artemis are not just to repeat the achievements of Apollo, but to go further by establishing a sustainable, long-term human presence on the moon, with a landmark commitment to landing the first woman and the first person of color on the lunar surface. The defining characteristic of the American approach is its deep and unprecedented partnership with the private sector. Instead of developing all of its own hardware in-house, NASA has embraced a commercial model awarding multi-billion-dollar contracts to companies like SpaceX and Blue Origin to build the landing systems that will carry its astronauts. This collaborative philosophy is legally enshrined in the Artemis Accords, a US-led international agreement that sets forth principles for peaceful and transparent cooperation in space. With dozens of signatory nations, it forms a broad coalition built on a shared vision, standing in contrast to the more state-centric models of its global competitors. Competition between China, US, and other nations. The geopolitical chessboard of this new space race is rapidly organizing into two primary alliances. In one corner there is the US-led coalition of nations that have signed the Artemis Accords, which includes established space powers like Japan, Canada, and the member states of the European Space Agency. In the other corner is the burgeoning partnership between China and Russia, centered on their ambitious plans for a joint international lunar research station, which is steadily attracting its own international partners. However, this is not a simple bipolar conflict. Other nations are carving out their own paths and emerging as significant independent forces. In a spectacular display of technical skill, India's Chandrayaan-3 mission made history in 2023 by becoming the first nation ever to achieve a soft landing near the lunar South Pole. This historic achievement instantly established India as a major player and a critical contender in the search for lunar water ice. The current landscape is a complex and dynamic interplay of national ambition, commercial interests, and strategic alliances. While intense competition is currently driving innovation at a breathtaking pace, the sheer crushing difficulty and expense of operating on the moon may ultimately force these rivals into a new era of global cooperation. The moon is no longer just a beautiful light in our sky, it's a destination, a resource depot, and a critical stepping stone to the rest of the cosmos. China's discoveries have opened a new chapter in human exploration, one that will challenge us technologically and force us to decide how we will explore these new frontiers together. What do you believe is the most important resource the moon has to offer? Share your thoughts in the comments. Don't forget to like, subscribe, and hit the bell icon for more explorations into the science and wonder of our universe. Thanks for watching Sci and Why.